So Therapeutics Data Commons is a library of data sets that are already prepared for machine learning. So all these steps we discussed yesterday of if we get data, is this data on which format? Do we know what variables we have? Do we know if all the smiles are readable, et cetera, et cetera? This is already done on Therapeutics Data Commons. You can go to their website. It's quite convenient. So we use example data sets from that. And then we'll use a few of the Python packages. First, we'll use the chemical checker that Miguel just presented to feature molecules, so to transform molecules into these signatures. Okay, so we'll see how this works in practice. And you'll see it's very fast, thanks to the work that Miguel and his research group did to implement this in Python. We'll use scikit-learn. Maybe some of you are familiar with this name. This is the largest, one of the largest packages for machine learning modeling. So they provide the algorithms, okay? So it's not like we're gonna have to develop the mathematical algorithms from zero. We can just import them from scikit-learn. And the third, you've already seen that yesterday, this is RDKit. RDKit has many functionalities to work with anything related to chemoinformatics, and we'll be using some of its functions again. Okay, so let's get started. Before I proceed with the presentation, I want to ask, so what, according to you, you can think of what steps we will need to do today. So what would be the first thing we do? And the second and the third. You can raise your hand or just speak up. For building a machine learning model. Okay, first step. Getting data, yes. So first step is getting data. I just showed where we are going to get this data from. From the TDC, yeah. Okay, so first step is to get this data. Very important on this data, Miguel just showed there are two types of models. So if you get data that is binary, so you only have zeros and ones, you will do which type of model? Classifier. So you can either classify molecules active, inactive, that's 0 or 1, active, inactive, or you can do what is the other type of model? A regression, yeah. So regression tells you the exact value, okay? So sometimes you only get data that is yes or no, active or inactive. In this case, we do a... Okay, I'm gonna be asking a lot of questions, so we can take a long time. So if we have data that is yes or no, active or inactive, what type of model are we training? Classifier, no classic, classifier. Yeah, it classifies in different classes or categories or groups. If we get IC50s, for example, what model are we doing? A regression, okay? So out of the top of your heads, what model do you think is easiest? A classifier or a regressor? Yes, so we'll start with the classifier. Okay, let's see if we get to the regression part. If we don't, it's on the notebook, so you'll have time to check it at home or later today. Okay, so we're gonna get the data. We're gonna see whether it's a classification or a regression, depending on what data we have. Then what is the next step we'll do? Yes, usually we would do that, but I just said that the Therapeutics Data Commons is already prepared. It's a database for machine learning. So everything we discussed yesterday, it's very nicely done for us. So we can skip this step, but yes. So usually you would get the data and clean it. So once we have the clean data, how do we go about training a machine learning model? Just think of Miguel's presentation. Yes, so we'll featurize, and I just show you as well with what. So what will we use for a featurization? Yes, the chemical checker. So just remember, there are many fingerprints, there are different types. Each one is more useful for one thing or the other. The chemical checker is particularly good for bioactivities. Yeah, because it encompasses all these large bioactivity networks that Miguel was showing. So we're going to use the chemical checker. So once we have the molecules featurized, what do we do? That's the easiest. What do we do when we have the molecule? Yes, so we take the algorithm and we train, okay? So we train this model. Once the model is trained, what is the last step that's very important and that we'll spend some time now on understanding? So you have your model, you go directly and screen new molecules and be happy about the results. You validate it, exactly, okay? So these are the steps that we are gonna do. We're gonna get the data, we're gonna use the chemical checker to filterize the molecules. We are gonna train a model and we are gonna see how it performs, okay? How good it performs. So let's continue. I think we are all here. We all went to Colab. Yeah, is someone not in Colab? Because we can go as slow as we need. I don't want anyone to get lost. Okay, so if you don't say anything, I'll assume we can go on, but just raise your hand and say it. Okay, so classifier. Miguel already presented this. Classifier identifies a new, at which category a data point belongs to. Okay, so because we are mostly talking about bioactivity in this course, we'll always identify active or inactive by convention, and that's very important, and you'll see why. An active is classified as a 1 and an inactive is classified as a 0, okay? So every time you find bioactivity data in the form of zeros and ones, 99.9999% of the times, 1 is active, 0 is inactive. Now I have an important question. If we are on the drug discovery cascade, if we have a model that predicts whether a molecule is active or inactive against Plasmodium, yeah, do we want to have a lot of ones or a lot of zeros? We want to have ones because we want to have actives, yeah? But if we are predicting, for example, cytotoxicity, we want zeros, okay? So 1 and 0 is not good and bad. 1 and 0 is active and inactive. For some models, active is what you want. For some others, active is what you don't want, okay? So just keep that in mind because that's important to interpret your models, yeah? Okay, so as I said, we're going to use a TDC data set. In this case, I chose one that is about blocking hERG. So we know that hERG is an important step in the drug discovery cascade because it induces a lot of cardiotoxicity. If some of you are not familiar, hERG is an ion channel, and if you block it, you can induce basically a cardiac arrest. So if the compounds block this channel, they are probably not going to be a good drug. Yeah. This is an expensive experiment. So that's why it's done later in the stage on the drug discovery cascade. But then many compounds fail. So it's good to have models to predict this activity. Okay, so again, in this case, actives means you are blocking hERG. Inactives means you are not blocking hERG. Okay, it doesn't mean that you want actives, you actually want inactives. So I prepared so that you don't have to look at all the code and get confused with that. Let me just share again the notebook. So we are in session 2. There is some explanation. You can click on here, it will bring you to the TDC data page. Okay, so we are here. We're on the classification tasks. The first thing we need to do, as we did yesterday, is to connect to Google Colab. So to Google Colab to Drive. So please, all of you, connect to your Drive. So I'm going to do the steps with you just to make sure I'm at the same speed. Okay, so while it's mounting, I think we can all understand this point for today already. So we are going to load the data set. Okay, so I didn't want people to get confused. So if you want, you can click on here. It will show you the steps. But basically, you can just click and it will start working, okay? So I'm downloading directly this data from TDC. The name is hERG, so that's the data set I want. And I'm saving all this into the drive, okay? So you'll have it on the drive as well. In this case, if you want to go, if you're confused or you don't follow because the notebooks are weird, you can always go to your drive and just check the Excels. That's easy to interpret, okay? But you don't need to worry about the code. So this is why it's hidden, but you need to get the tick. Okay, so now we've loaded this code. So again, Mikel shared a bit of information about train, test, and validation steps. So if I go back to the presentation, yeah, this is what's happening inside this cell. Is everyone finished with getting the data? If someone is not, raise your hand. Okay, Godfrey, are you stuck, or maybe Mikel or Jason, you can check. Okay, so meanwhile, if everyone has their data, and we click on the cell that says print the length of train, print the length of the validation, print the length of the test. You see three numbers. Can someone tell me these numbers just to check that you are all there? Which numbers did you get? Exactly. Okay, so in this case, because as I said, therapeutics data commons is already very nicely separating the data set for us. If this was a real exercise, we would have around 700 molecules, and we would need to think how we split them. Can someone think about a problem you might find when splitting data based on what we did yesterday on the chemical space? Andrew? Can you speak a bit louder? Exactly. You may want to exclude some compounds that are weird, that are very separate from the rest. So that's one thing. What else? Compounds that are more soluble. What do you want to do with them? You want to have them all in the training set, all in the test set? What do you want to do with compounds that are more soluble, for example? Training set. So if you put all the compounds that have a specific characteristic on the training set, then your chemical space for training is limited to that set. So if your training set and your test set are very different, this is maybe not the best idea, right? So what we want to do when we have our data set is to check how we split it so that it's more or less equally split. Yeah, so this will help on the model training. We don't have to do this step because this is already done. So what we have now is a training set of 458 compounds, a validation set of 66 compounds, and a test set of 131 compounds. Now, can someone tell me the difference between the validation and the test sets that we can explain in the previous presentation? Bonnie? Yeah. Yes.
Is it okay to add more compounds, more test compounds than the ones used
to train? So if you do that, it's because you have so many compounds, like so many, that you don't care, right? Because you need quite a lot of compounds to train a model. So if you put more compounds on the test set, in this case, it wouldn't be possible because then you would leave your training set with very few data points. So usually what you do in reality is you do this split, you validate your model, you fine tune it, you make sure it works. And once you're 100% sure of the parameters, you train it with the whole of the data. So with the 700 compounds, and that's your final model. But then you cannot do validations or anything because you don't have test data. So is it too complex? So you typically never have a test set larger than a training set because most of the data will be used for training. Okay, that's it. Okay, so can someone, is there any other question at this point? No? No questions, worries me? Means you're not following? Okay, can someone tell me the difference between a validation and a test set? Eh? The difference between both tests, both sets. It has to do with overfitting in May, but why do we use when do we use validation and when do we use a test?
For me, I think that the training test is the bigger
Yes.
goal that we have, right?
Mhm.
And then the validation one is the one that we know the data, but we didn't expose to the training model.
Mhm.
So when we done the training, we can actually check to
Yes.
see if the model actually give us the value that we know that we call the validation set.
Perfect. And the test?
Then once we're done, of course, in that bigger set, there's a bit of set that we put aside in order to see if it's bigger. So we can actually see if our model can actually recognize our validation set.
Yes, so that's the basic of it. Perfect. Thank you so much. So if we look at this, the train set is used to train a model. I think everyone is clear on that, right? So we have the largest chunk of our data. Then the validation set is used to improve the model, okay? So what I do is I train a model, I check how good it does, I do some changes to make it better, I check again, I do some changes again, I check. So I start a cycle here. Once I'm very happy with this, I still need to make sure that all these changes I did didn't cause anything like overfitting, so that it's not adapted to this specific set, not that it's usable in a larger data set. So that's why then I have the test set, which is used to evaluate the final model. So I train, validate, improve, validate, improve, validate, improve. And once I'm happy, I go with the final model and check on something that the model has never seen. Is this clear? Okay.
So how exactly do you choose compounds for say training and validation? Like if I'm putting it this way, I'll say maybe if there are compounds that have been experimentally validated, there are those that have been clinically validated or clinically active. Say that you would use maybe compounds that you know clinically are relevant. There's a validation set, and those ones that are used that are data or experimentally are the ones that you use for training.
Yes, so in this case, I'm assuming this comes from a single experiment. So this may be an in vitro experiment, and I get all the data from this experiment. Usually, if you have compounds that are clinically validated, this would be on the test, on the final model performance. So things that you know from other sources that are really good, these you can use on your test. Yeah, but they are not used on the model training or validation, because usually model training and validation comes from a single data set or a few data sets from the same conditions, let's say. Yeah. Yes.
Yes. The validation test sets, how do we really choose them from? Let's say everything comes from the same experiment. I understand that they usually say 80%, 20%, and then 20% testing. But the validation set, how do we explain it? Does it come from trained data or it's actually isolated?
No, so if we have here, if we say we have 100 molecules, so you would put 70 on the train, 10 on the validation, 20 on the test. So it's a 70, 10, 20. Yeah. Okay, so is the concept clear on train, validation, and test? Okay, more questions.
Yeah. Why is the validation
Because you want to have, yeah, so you want to have enough molecules to really be sure. They could be the same size, this and this. So this is, it depends a bit on the data you have. If you have tons of data, you can make the splits that are more equal. If you have less data, you need to prioritize. Yeah, so Having 100 molecules on the test set is like nice. We'll see the graphics that we create is like a good measure to know how good is your model performing. So that's why it's a bit, this one is a bit smaller. But if we had like a ton of data, we may have them more equal.
In that case, do we give you the ratio for the training, validation, and test?
The ratio, yeah.
The ratio.
So I would usually say 70% train, 10% validation, 20% test. But again, it does depend on your data set. Yes. So it was Chris first.
How do you rationalize which data to choose for the training set versus the validation? So like the first round of training the model, how do you know what for?
So, it depends on the problem you are having. So as a general rule, I would say as homogeneous as possible. So have the three sets as similar as possible so that there is no outlier points. Yeah, so that your test set is not different from your training. But then again, it depends on the problem. If you want to make models and you want to test that they are good for predicting new series, that they are applicable, you may actually want to have your test set a completely different series that you know the results for, and then you test if your model that is trained on other series is actually good on this new one. So for basic modeling, have them as equal as possible. For more advanced questions, like, okay, I'm gonna be able to model new series. Is this model good for this new chemical space? Then you would do it a bit differently. Yeah. Frank, do you have a question?
I'm going to ask about the actives and effectives.
Yes.
If you want to maintain the same ratio within all sets.
Yes, that's so very important, and I didn't say it. Thank you. Of course, you want to have as much as you can the same proportion of actives and inactives across the three sets. Yeah, for sure. Thank you for the question. And just think, we are now talking about molecules, but these are basics of machine learning. So with any type of data, like this is like the basics. So any type of data that you use for modeling, any type of activity or prediction you want to make, this is like the same. It's not only for chemistries or everything. Can I have a question? Okay. Okay, so let's move on a bit. We can, like, there is no rush, so we can take as much time as we need to answer all these questions. It's great that they are coming in, so please keep asking. Otherwise, I feel like I'm going too fast. So we proceed. Okay, so this is an important thing because we will not be doing rounds of optimization because we don't have the time. For now, we won't use this, okay? So we'll just focus on the train and then evaluation on the test set, okay? So for this example, just to make it simple, we will not be doing these rounds of making the model, improving it, and so on and so on. So we'll just make a model and check the performance, okay? So validation is very important that you understand the concept because many papers refer to that and you need to know these splits, but we are not going to use it today. Okay, so we have our data. We know that it's 400 and something compounds, 66 and 100 something compounds. So something we can do, you can run these cells. So let me put the notebook maybe just so that we are all on the same page. So we can run, let's explore how this data looks, okay? So the head command is just telling me, as you can guess, head, show me the top. Okay, show me the head of the. So this is the data that Therapeutics Data Commons has provided me us. So the name of a drug, the smiles of a drug, I can tell you it's already canonical and nothing goes wrong, it's very nice. And the why, what is this why?
Binary data, straight data.
Exactly. So in this case, these 5 compounds that are shown here, do they block her or do they not? They block her. Okay, so we have, these are only the first 5 compounds. The list goes on to the 400. And we already have our data very nicely, so we only need to care about the smiles and the binary data, yes or no, okay? Moreover, because we are using this, we can easily, you could go on Excel and say, okay, show me how many ones or how many zeros to count. But with Python, we can do it very easily. So here, I'm asking, show me the length when the Y is 0 and the Y is 1. Okay, so we have 148 compounds that are 0, 300 that are 1. So this, someone asked this on the Slack channel. And this is not what we usually have. So usually we have more inactives. Like if we are working in Plasmodium, we usually have more inactives. In this case, many compounds are cardiotoxic or predicted to be cardiotoxic. Therefore, we always have more actives than inactives, okay? So what else can we do? Let me continue here on the notebook. So everyone is clear up to here? Okay, so before moving on to model training, I just wanted to show you some things you can do very easily. So we are going to use, just click here while I'll talk because RDKit needs to be installed. So this RDKit package, this chemoinformatics package has many functions. One of them, which is very convenient, is to draw images, draw molecules. So what I'm going to tell him is, okay, take the smiles. So again, the smiles here are the drug column, yeah? So not drug ID, which is the name, but the drug column. And just take a few. In this case, I just asked for the last 9 molecules. I think because they look nice. So we have a list, okay? So we get this list of 9 molecules. We have these smiles. And then we need to convert them to something RDKit calls molecules. So molecules from smiles, this is something we don't understand, we don't need to worry about. It's just a step that needs to be done every time we work with RDKit. So RDKit does not understand the smiles, it understands moles. So it takes the smiles, converts them to moles, and then using this function called draw, which you can imagine what it does, voila, it very easily plots our molecules. So we could do this for the whole list and get a very fast visualization of our molecules, okay? So these are the bottom 9 molecules that we have in our train set. Yes? Again, don't worry about the Python itself, it's just for you to understand what can we do with Python. You don't need to understand the language as of now. But basically, we have a tray and a test set for which we have smiles and activity data. Yeah? Okay, so we got our data. Step 1, we got our data, we clean it, we didn't have to do much, it was done, and we split it into train and test. So what is the next step? Exactly, filterize, okay? So while I talk, we can click on here because it needs to load. It may take a while. This is a very large machine learning model that we are using. So let's leave it loading, okay? So basically here, what I'm asking Colab to do is to fetch all these models from Mikael's repository, and we can directly apply it. So we don't need to do much. While it's fetching, let me see if we are done with the slides. So, okay, we have this. We have the images. Okay. Yes.
Like when you are talking about the cardiotoxicity, like active or inactive,
Yes.
like we know in different disease areas and also in different phase of drug discovery. So the cardiotoxicity value varies. So you have to pre-populate that criteria before you start the experiment, or it is something like that.
About the cutoff, you say?
Yeah.
Yes. So that's a great question. So you have 2 scenarios. Scenario 1, it's your own data. You want to do a classifier, but you have the original data, and you can decide the cutoff. And you say, okay, so I want to create a model for a 10 micromolar cutoff, for a 0.1 micromolar cutoff. But many cases like this one, the authors of this data set, they did not provide the data. So if I'm not wrong, that's a 10 micromolar, but you need to go back to the original publication, check the cutoff, and there is not much you can do because they don't provide the real value. So if it's your own data, you can play with it. If it's not your own data, that's what it is. But yeah, that's a very important question. Thank you. So basically, checking always the original publications and trying to understand the models is what is most important. Okay, so again, characterizing is converting smiles into vectors or images, in this case, vectors that can be passed to the machine learning model. Okay, so we are installing the signaturizer. In my case, it's still loading, also yours. Yeah, okay, it takes about 3 minutes. So when you get nervous and are like, why is this taking so long? You can check here when it's executing, it's running things, so it's working. It usually takes a bit less because it's all of us connected on the internet. It may just be a bit slower for everyone, but it should take about 3 minutes. But so meanwhile, let me explain this second part of the command. So I have the smiles. As you can see, the output is called already Y. Okay, this is convention. The input of a model is called X, whatever that input is, X. The output of a model is called Y, always. Okay, that's not only in the case of chemistry, it's by convention in mathematics, the X and the Y of the equations. Yes, so it's the same concept. So we usually call it, okay, if you get this error, don't worry, it's an internet error. So just run it again. Maybe? Yeah? Okay, so this, who has it loaded? Okay, so the rest of this room that got crashed, we do it again one more time. You wait and then you do it. Let's see if it works this way. While it's running, let's just click on it and wait. Hopefully it will work. So by convention, again, X is the input, Y is the output. So are the smiles the input of the machine learning model? Are the smiles the input of the machine learning model? The input of the model? What is the input of the model? The signatures. Yeah, the smiles cannot be understood. So smiles are not the X. When we name something X, it's already the signatures, these numbers, zeros and ones and whatever it is. Yes? Is everyone following on this? Okay, so this is why I named this data set X train and X test. So on the X train, I'm converting the smiles of the train set into signatures of the chemical checker. Okay, that's just the notation I use, like the Python. And the X test are all the smiles converted to signatures for the test. So maybe I can use one of these. Just to be, well, anyway, everything is going. You can leave them. So, this is, it's done?
Yeah.
Okay, so now this row, this ones, if you didn't have it loaded, just click on it again and see if it works. So for the train data set, we have smiles. Okay, I'm just gonna write very simple smiles. So we have smiles, thank you, all the way to 400. We have the Y, the real Y, okay? We can even call this real just to be sure. It's the real one, the value I know is true. This is 1, 1, 0, whatever it is. So now I need the X, what I'm gonna use for the model. So I take these smiles, and I use the chemical checker, which is very easy to use, as you see. And I get the X, I call it X train, because it's the X from the train data. Okay, so basically, instead of having a list of smiles, I will have now a list of vectors. See? Yes, a vector is a number. Okay, I'm just going to write zeros and ones, but it could be other numbers. So it's 0, 1, 1, 0, anything, and 1, 0, 0, 1, whatever, a third one, and so on. Okay, so instead of having this list of smiles, I'll have this list of numbers. But it's like if I put it in a table, I would see it like this. Yeah. And I have the same for the test. So same idea. I have the smiles. I have the Y, the real Y, the one I know. So the CCN, CCOC. And I have the X, in this case, I call it X test. Y test, because it's the test set, okay? So I have a list of numbers there. Yeah? Okay. So was everyone able to load the chemical checker without crashing? Great. So I have this tick here, which means it ran in only 1 minute. So you see how much better when we like divide. Yes. So maybe Michael, you can answer. Like, so when I then click, I can see here how you can also do this. Now it's already loaded, so it won't have internet programs. So this is converting, as you can see, it's generating the signatures for the 458 compounds and for the 131 compounds. Yeah, so it's quite fast for the amount of data it's collecting. And I wanted to just show you one. So the first molecule, what is it, this signature that we just created? Well, it's an array. It's an array of numbers. So it's a set of zeros and ones, a bit more complex. So this first molecule is now represented by all these numbers. Okay, it's quite long. What is the default now? Huh? Okay, so it's 3,000 numbers. So these 3 dots is a lot of numbers in the middle. Okay, but we are basically here, we've converted this CCCC into this very long list of numbers, and we've done this for each molecule of the set. So if instead of the 0 I write, I want to see molecule number 10, that's another vector. Molecule number 400, that's now another vector, okay? And the last step here, this you can understand. So instead of having just Y, so Y and Y is the same, so I can differentiate them. So I'm calling them Y train and Y test. Yeah, just by convention. So now we have Y next. Yeah. So just run this last cell just to change these names. Okay, so let's go back 1 second to the presentation and make sure everyone followed. So this is just what we did. Okay, get these arrays. Okay, so which data do we have so far? So it's plotted there, but I would like someone, or a few of you, to tell me which kinds of data have we seen so far and the names they have, so that we are all on the same page. So which data sets do we have? What are they named? Anything of the things that we've seen so far. Okay, so training data, that's very general. What do we have inside training data? how are they, like what types of data, how are they called? So the binary data, how is it called? No, wait. Binary data. Okay, so we are on the training set, binary data. So how do we call the binary results? The binary results, zeros and ones? Eh? Yes, that's the Y. The binary results, so zeros and ones that represent the activity, these are the Y. In this case, I name it Y train and Y test, okay? So we have binary results. We have a Y train and a Y test, that's zeros and ones. What else do we have? What is the X train and X test? The signatures that represent what? The smiles. Okay, so are we clear on the notation? We have the smiles, the original smiles that we won't use anymore. They are just because we chemists and biologists cannot understand numbers, so we need the smiles. We have the Y's, Y train and Y test, which are the binary activities, active or inactive, and we have the X, which is the representation of the smiles, the featurization. Yes? Any question here? Yes, yes.
In terms of determining whether active or non-active, is that something that the data has already been categorized?
Yes.
And how does the value?
So this depends on your data. So if you're an experimentalist having your own data set, you can say, okay, so for this type of, I'm interested in having this cutoff. I think for plasmodium, it's usually like what, 0.1 micromolar activity. So you decide and then you just transform all your data. But for this case, we don't have the real data. So we would need to go back to the original paper and read what type of threshold they used to convert from IC50 or whatever they were measuring, I don't know, to zeros and ones. So it's very important to understand the data, to really look into it. You can actually later, the application is linked, so you can go and check what they do. Yes.
As signatures or the signature
Yes.
module, does it work similar to that one that general experience?
It's the same idea. What we used yesterday with JSON was a basic fingerprint generator. What we are using today, just because Miguel explained it, and we thought it was nice to then apply it, is the chemical checker, which are the same but more complex. So they condense more information. That's why they are not zeros and ones, but more like longer numbers.
So it captures 1D to 40.
Yes, the particularly interesting for the chemical checker is that it captures biological information, not only structural. So it's quite powerful. Right? Any comment you want to make on this? So it's the same idea as a fingerprint, it's just more complex, and we call it a signature, but it's exactly the same. It's a way of representing the molecule.
Gemma.
Yes.
So can I take away just a follow up one question that she asked? So if you have no real data, have you ever come to a situation where you find it difficult to actually draw that binary line? From my experience, it seems sometimes if you draw a line and the difference is like 0.01 or something like that. So I tend to say, can I have beyond binary? Have you ever come to that?
Yes. So if you wait a bit, let's see actually how we can. So we do classifications first before regressions because they are much easier, and usually for regression you need more data, and otherwise they are not so accurate. Okay. So just let me proceed because you'll see the output, and then you'll have kind of an answer to this problem. Okay. So the data we have so far, the original data, we have smiles, with its associated activity. These are, and we divide it into train and test. Then we've converted the smiles into this X train and X test, which are the representation of the molecules. And what is the third type of data that we have? No, we forgot about the value. We are not using it. So we have the original data, the X train and X test, and which other data? The Y, exactly. So we have the Y test and Y train, okay? The results I know are real, are experimentally tested. Okay? I see some faces like no, so you can just ask more questions, think about it. Okay. So do we proceed? Okay. So let's continue. Let me just go along with you on the notebook. Okay. So we're going to use, as Miguel was explaining this morning, supervised machine learning, right? So we have, for you to imagine, we have these numbers, the 0.3, 0.6, whatever, 0.7. This is one molecule. This is another molecule. Okay, we have all these molecules, and we have its outputs, ones or zeros. So now we are going to train a model, a neural network, okay, that's very complex. You don't need to understand what happens inside. But basically, we want this model to learn. So we input this, and it knows that this is the output. So this needs to learn. So that when we come with a new molecule that is different, so I come with a new molecule, I print it here, and I ask, what is the result? Okay, so we are now going to do this step. I input data, and I tell him what is the output, so this model can learn. I'm talking about the model as if it's a real person. So it can learn. This may seem very complex. It's not, because we have the functions that do it automatically. So just first let scikit-learn load, okay? And we're going to use something that is called a random forest classifier. There are tons of algorithms for machine learning. We won't go into details today because it's like completely out of scope. It's more mathematical. It's just one of the typical ones, a random forest, okay? It's called random forest because if you look at its organization, it has like branches, okay? So that's the name if you want to remember it. So, okay, I say, okay, I want a classifier, which is a random forest classifier. And the process of training in machine learning is called fit. So always when you see fit, it means you are training this model. So I'm fitting using which two data sets? Is everyone understanding why we use the X train and the Y train? So you can just let it be fitting. So we are telling him, okay, fit these molecules to their output. So these molecules, this is what is this? The X train, and what is this? Y train, okay? So I'm just telling the model, okay, take these vectors and learn if they are ones or zeros, so that when I come with a new vector, you can tell me if it's a 1 or a 0. Yeah, that's what's happening in this fit. It's very easy. A lot of things happening in the background, but that's basically it. Yeah, is everyone up to speed here? Cool, we have plenty of time. Yes, okay. So we have our model. So now what would you do? We have our model, we've fitted it. So what's the next step that we've discussed? Okay, so now we test it with which data? The train data, okay? So of all these things, what do you want to give to the model? I'm going to give what to the model now? the X strain, the model is already trained on the X strain. Do I want? I want the X test. So I want now to input these molecules, see what is the predicted result. So if I call, how would I call the predicted results? Let's be imaginative. By convention, the results are usually called with which letter? Y. So if the ones that I have here are the Y real, the ones that the model predicts are the Y predicted. Okay, so Y pred is what the model outputs. It's the Y that is predicted, not real. So I'm gonna test these molecules. I'm gonna get a predicted number, and I'm gonna see if it's the same or not. If it's the same, the model is perfect. If it's very different, we need to do some work on this model. Yes? Okay. I wish things were that easy. So now it will be a tiny bit more complicated, okay? So instead of giving a 0 and a 1, and this is very important, a classifier outputs two numbers. The probability that a molecule is 0 and the probability that a molecule is 1, which is not the same as being 0 and 1. It's a probability. Okay, so I have two numbers. So we'll now take time to understand this, but basically what I do is, okay, we said we'll call this Y pred, yeah, the prediction, and I'm predicting the probability of which molecules? The test, yes? And here I'm just showing you the first 10 molecules, just to have an example. Okay, so we get this. What is the first column? Okay, and probability of 0 inactive, and probability, I'm gonna just change this. You need to change it on yours as well. My apologies. Okay, so the first column is always the probability of 0. The second column is always the probability of 1. And can you tell me something about this, just seeing at the data? About these two probabilities? So for the first molecule, actually the second is even easier. Yeah, this probability is always equal to 1, okay? So of course, if a molecule is 49% likely to be active, it's 51% likely to be inactive. So if the molecule is 21% likely to be inactive, is 79% likely to be inactive. Yeah, they are complementary, they add to 1. Donald, do you have a problem? Yes, of course, because it's a model. So you predict, like the model, it gets trained every time, so it will be slightly different, but you'll see that the performance shouldn't be that different. So yes, it's very important. You won't have the exact same numbers because you are training and predicting, so your model may predict a bit differently. If I run it again, I'm sure I may also get it. Yeah, so let me just do this. Get the same. Okay, so what do we want? Analyzing the two, does it make sense to always keep the two probabilities? So the result is two columns. First column is probability of inactives of 0. Second column is probability of 1. So does it make sense to keep both columns? Why not? Yes. If I have one column, I can actually know the other. So we just take one column. And which column do you think we take by convention? 0, probability of 0 or probability of 1? Yes, you looked at it. It's written there. So we usually take the probability of active Y by convention. Okay, so we don't want column 0, we want column 1. So this is what I'm doing here. I'm telling keep only the column 1, not the column 0. Okay, so just run this, and if you run it, you'll get this. So these are all the probabilities of my molecules on the test. So how many molecules should I have here? Do you remember? No, we are on the test set. 131, exactly. So these are the predicted probabilities of being active for my 131 molecules. Yes.
It's like, how to the machine calculate the probability? Like, is it possible, like, first time, if I run, the probability is like 37.3.7, and then second time around, it is just opposite. Is it possible?
I think it wouldn't happen. Like, it would have to be a very random model, like something that is trained on very, very random data, and then you would get whatever. But usually, if you train your model, you will always get the result. So let's go back to the presentation 1 second, leave your notebook, because now that's the last part. We have 30 minutes to do this, and we can take as much time as we need, and we can go as slow as we need. That's the key of today's session, is to understand how do we evaluate these models, because it may happen that you run models made by other people or that are on the internet, and you need to know how to interpret the results that you get, okay? So that's the key part of today's session. Okay, so let's summarize. We had our X, our inputs of signatures, and our Y's, our outputs, activities against health. We trained what we call a random forest classifier. Okay, this is the text that we use. We fit it to the train X and Y. And then we get probability of 0 and probability of 1. So when we predict our X test, we get our Y pred, which is these columns, and we want to keep the second column, yeah, the probability of 1. Is it clear? Is everyone up to speed here? Questions? Yes.
Is it not always advantageous to have both columns, particularly for scenarios where it's whatever reason, probability is 0.5 and 0.5. It's on the borderline, say 0.49 and 0.51.
Yes.
How do you then get to confident that sign that is effective?
Perfect. So we'll show that now. That's a very good question. So now we have probabilities, which is not a 0 and a 1, which is something that we all understand. So what do we do? Okay. This is the key with a probability classification model, is to set a cutoff. So by convention, if you don't know anything, the cutoff is set at 0.5. Okay? But we can say, oh, but I want molecules that are really just the highest predicted. So then I can put my threshold a bit higher. But I want many molecules. I don't want to lose any actives. I can bring it down. Yeah? So let's do this little exercise. So, first molecule. These are the probability of 0 and the probability of 1. If I set a cutoff of 0.5, is it a 1 or a 0, the output? If I set a cutoff of 0.7 and a cutoff of 0.3, okay, so we have a 1, a 0, and a 1. So in this case, this molecule is predicted to be active, but it's not the highest on my data set. So maybe I don't want to pick it. For the second example, cutoff at 0.5, what do I get? An active or inactive? Okay, I see both answers. So 0 or 1? Cutoff at 0.7. That's a tricky one. In this case, let's say it's cutoff larger or equal to 0.7. Okay. And with a cutoff of 0.3. Okay, let's see what Gemma was thinking. Yes. For this molecule, cutoff of 0.5. Okay, 0 or 1? 0. Cutoff of 0.7. Cutoff of 0.3. Okay. And for the last molecule, that's the easiest one. All ones. All ones. Okay? No? Okay, so ask me what you don't understand specifically. Okay, so the cutoffs, you decide. You decide depending on your problem. So if you have, for example, an assay that is very, very expensive to do, you want your molecules to be, so you prefer to have molecules that are real actives, or you prefer to be able to not lose any potential actives? What do you prefer? Let me rephrase the question. I have an assay that is very expensive. I have 100 molecules. I can test a few of them. The few that I test, do I want to be sure that I get all the positives, or that the ones that I test are positive? It's a bit different. Do you understand the difference? Also. So, if we have a list of molecules, okay, molecule A, B, C, D, E, F, G, that I have ranked according to my model, yes? So I use the probability of 1. So let's say this has a probability of 0.9, 0.88, 0.79, 0.65, 0.5, 0.49, 0.8. Okay? And then if let's assume that I know the results before doing the experiment, okay? So I know this is a real, so the real result, this is a 1. This is a 1. This is a 1. This is a 0, and this is a 1. Maybe because my model is not perfect, so it doesn't, so it has classified this molecule better than this one, but it's actually a 0, and this is a 0, and this is a 0. Yes? Is this clear? So if I set my cutoff at 0.5, what will happen? I set my cutoff at 0.5. So how many molecules do I screen? Okay, so if I say, okay, I set my cutoff at here, so I consider this is the real, let's do the predicted here, sorry. The predicted at 0.5 is a 1, a 1, a 1, 1, 1, 0, 0, yes? So, because I only have my model to decide, I say, okay, I'm going to screen these molecules. What do I find? Not too bad. I find 4 molecules that are real actives and 1 molecule that is an inactive. But I didn't lose any actives. I found all the actives on my data set. Yes? But now, if I say, no, this experiment is very expensive. I want to do very few molecules, but I want to be very sure. I say, my cutoff is going to be 0.75. 0.75. So 0.9, I would predict this is a 1. 0.88, predicted as a 1. 0.70, I predict it as a 0. This I predict as a 0, as a 0, as a 0, as a 0. So in this case, how many molecules do I test? I test 2 molecules. How many actives do I find? How many non-actives do I find? Great, because I wanted to find actives. Now, how many actives did I lose? Now, how many actives, real actives, did I lose? Yes, I didn't screen C and I didn't screen E, which are real actives. I discarded them. So sometimes you want to screen a lot of molecules just to find all the possible actives. Sometimes you want to screen very few molecules just to be sure that what you're finding are actives. It depends on your situation, on your experimental requirements, on the problem that you are facing, on the stage you are at in the drug discovery cascade. Yes, so probably if you are in a hit discovery phase, you want to test everything, but just find as many actives as possible. But if you are already optimizing a few hits, you maybe just want to keep what is really working nice. Yes, we'll do more exercises on this just now. But is this clear? So, is it clear? Not sure. Okay, we can talk about it later with a notebook. Okay, so we'll just finish with the confusion metrics. So how do we analyze this in an easy way, no? Like these tables are very ugly. So how can I easily see that? This is called confusion matrix. So I have on this side the true values, the true active and the true inactive. On that side, I will have the predicted actives and the predicted inactives. So now I just put values. Where is this? So if I have, let's use this example with a cutoff of 0.5. Let me just draw it nicer for everyone to follow. So let's use this example, okay? I have molecule A, B, C, D, E, F, G. I don't know the auxiliary in English. The real results are 1, 1, 1, 0, 1, 0, 0. Yes, this is my test set. My probability of 1 is 0.9, 0.88, 0.7, 0.65, 0.5, 0.49, 0.3. This is the probability. And I decide that I want to do a contingency table just to make it a bit more interesting, a contingency table with a cutoff of 0.75. Okay, so if I have used a cutoff of 0.75, this one is an active, this one is active, inactive, 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 inactive. Now I can't do this for all my data set, I'm gonna die. So molecule, so now I'm gonna just write here the names. Okay, so this is the same schema. This is inactive, active, this is real. This is inactive, active, this is predicted. So molecule A, where does it fall? It's a real active and it was predicted to be active. So real active, real active. Molecule A goes here. Molecule B, it's a real active and it's predicted to be. Molecule B goes here. Molecule C, it's a real active and it's predicted to be. So where do I put it? False, negative. It's a real active, but it's predicted to be inactive. Molecule D, it's a real inactive, but it's predicted to be inactive. Yes, so it's a real inactive, and I predicted it inactive. So did I do good? Yes, it's a real negative. Molecule E, it's a real active, but I predicted. So it's a real active, predicted inactive. False. It's a real active, predicted inactive. Negative. False, negative. Molecule E, it's a real active. Okay, no, sorry, I need, okay, D, sorry, this is it, so we are already on that. It's a real inactive and predicted. So where do I put it? And G, same. So this is how you construct these matrices, okay? And this is a very easy way to see how our data is distributed. Yes? Good. So let me just, oh, this is not working. Continue here. Okay, so last concept of the day, which is precision and recall. So these matrix completion matrices are summarized in two concepts. Precision, how many positives are actually positives? So at what column I am looking? What is my interest columns here? The positives. So how many of all the predicted actives, so sorry here, of all the predicted actives, how many are real actives? And I also have the other measure, which is okay, now we don't look at this. Sorry, I made a big mess trying to. We won't go over all this. This was just for. Okay. Sorry. So, precision. We look at this column, actives. How many real actives do we have of all that I predicted active? And recall, how many positives I was able to identify. So of all the real positives, which ones I was actually able to identify. So now I'm going to make you a question. Is it possible to optimize both measures always? Is it always possible to have the high recall and high precision? It's up to a point you can improve your models, but there is a moment where the model, you either want a high precision or you either want a high recall. And how you determine if you want a high recall or a high precision? With your cutoffs. So if we want a high precision, we put a high cutoff or a low cutoffs? A high, because we want to identify real positives. So how many positives are actually positive? If we put our threshold low, we're going to get a lot of positives, but many are going to be false positives. If we want a high recall, so I want to not lose any actives, what do I set? A lower cutoff. Yes, so there is a balance between both measures, of course. You improve your model so that they have the highest recall and precision, but up to a point, you need to decide what is more interesting to you. So if we put a more restrictive threshold, we have a higher precision. If we put a lower threshold, we have a higher recall. Okay, so let's finish going back to the notebook. So model evaluation. Okay, the cells are hidden, so just unhid them. and just click on the first one. Luckily for us, you are gonna get the numbers a bit different from me, but Learn already provides us with a computation of these matrices, so we don't have to do them by hand. Just know that if you use the default, which is what we are using now, the cutoff is, what is the default cutoff I mentioned? 0.5. Okay, so these matrices are built with 0.5. If you want to play with it, you need to play with the function itself. It's easy to do. We are just not doing it now. But I just wanted for you to see. So do you think this is a good model or a bad model? Okay, to predict positives, is it a good model? Yes. To predict negatives? Not so much. So this model, I mean, we haven't done any testing. And can someone tell me why this model is so good at predicting positives? No, not for the cutoff now. Let's forget about the cutoff, but the bias of this data, and I mentioned it several times. What happens with haired data sets? We have more actives usually, and the model learns better for actives than for inactives. Okay, so just to finish as an exercise, we already gone through this question. So if your experiment is very expensive, you want to test high precision. If your experiment is not expensive, you want a high recall. So this is what we got. Now we got a bit different numbers because I trained the model again. So, but now with using this, let's just use the numbers on the screen. So just to make sure that everyone understood, let's calculate the precision and recall for these numbers. So for the precision, what values do I put? So on here, denominator. True, positive, so predicted one and real ones, 93. At the bottom, and for the recall, $16 or $17? Who thinks it's 17? Raise your hands. Okay, raise your hands. Who thinks it's 17? Raise your hands. Who thinks it's 16? Okay, no one raised their hands, so we can't go on like this. So again, just have 30 seconds to think alone, and I'm going to ask the question again. There is no wrong answer. The only wrong answer is not answering me. So, okay, let's do this again. Who thinks it's 17? Raise your hand. Who thinks it's 16? Raise your hand. What is happening with all these rules? Are we lost? If you are lost, you tell me. Yes, question. So they can see.
The false positive. The false positive. Told right. Yeah. So it is not 93 plus 17. This is
Yes. Sorry, I was not seeing this. I trusted this program. Sorry. So let me use this one there. Now it's my fault. Okay. So actives that are predicted active, true positive. Inactives that are predicted active, that's a false positive 17. So false negatives. Sorry. No. Thank you, Petrus. Okay, so let's see. I don't know why I put this 5 here. Huh? Okay, don't worry about the 5. I don't know why I put here. Anyway, the good thing is that we don't have to do this manually. You can easily calculate it with these functions that are called precision score and precision recall and recall score. And what I did here is I did it manually. So you can see that here I'm setting the threshold, but I could change this threshold. Like I did this a bit manually, so I can change the threshold. And now I could put 0.7 and see how this changes, 0.6 and see how it changes. So that's how I evaluate models. We can, do we do the rock here before lunch? Huh? Okay, so it's lunchtime, but we started a bit late. So there is only one more concept to learn, but I don't want to overwhelm you. Are you ready for one more concept? Okay. Oh. Last thing of the day, of the session. Just as a recap then, we have our train and test data, which we've converted to X signatures and Y outputs, ones and zeros. And now we have the predictions. So the prediction, we have the output of the classifier, which is probability. Okay, remember, it's a probability. And we can binarize it. So what we have done here is when I set a cutoff, I create a binary result, a 0 or a 1. It changes depending on the cutoff that you choose. Yes? So are the contingency tables easy to interpret at first sight? What do you need to know to understand a contingency table? If you don't know the cutoff, can you interpret a contingency table? No, that's why they are not so great unless you have the cutoff. So if you just see these numbers, like you see the precision and the recall, but you need to read a bit more, so it's not that straightforward to interpret. So we would like to have a way to understand the performance of our model if we just have if we don't know anything. So just by seeing it, something that does not depend on the cutoff that I choose, that can already tell me the performance. Yes? This is a bit complex, so we won't go. Don't worry if you don't understand how these are built. We don't need to understand how these are built now. We just need to understand how to interpret them. So what we use to understand the performance of a model, if we just independently of the classifier of the cutoff, is what are called the ROC curves. I'm sure some of you have heard about them. I'm sure many of you have seen them. Yeah, so it allows you to know the performance of the model in general, regardless of the threshold. So I'm gonna skip this because that's a bit of concepts that we don't want to go over now. But basically, if our model was perfect, our line would go over like this, and the area under the curve, so this is our curve, the area under the curve is everything, so it's a 1. If our model doesn't work, it's not able to discriminate between positives and negatives, actives and inactives, our line would go completely diagonal. So the area under the curve, all this space here, that would be, what is it? Which, if all this space, it's 1, if my model is not good, this space is 0.5, okay? So what I usually have when I evaluate a model, it looks like this. Yes, so I'm sure some of you have seen these curves. So basically, the closer this curve is to the perfect, the better the model it is. If this curve is negative, you may just be switching, like you may have switched zeros and ones at some point. But usually, so you get a value that is between 0.5 and 1. And by convention, if it's above 0.65, above 0.7, it's quite a good model, okay? So let's see what we get for our model. So we just need to understand that the closer this line is to the top, the better it is. That's it, easy. So let's go to our notebook, finish. So you can see here how I tell, we just want to import a rock curve. So I get this rock curve, and I get an area under the curve of 0.83. You may get a bit different, but around 0.8 probably all of you. So do you think this is a good model?
Yeah.
Yeah, so this is not a bad model. We didn't do any changes. We didn't make any corrections. It's that good just natively because we are using data that is prepared for this kind of modeling that has been curated and cleaned from the TDC. So that's why just out of the box, it's so good. So don't repeat this exercise at home. With your knowledge, you need to do a bit more work. But basically, so when you see papers related to machine learning, most of the times they are classifier models, and all of them have this type of curves. So you need to understand what it means. So the closer to here, the best, and the larger the area under the curve, the better as well. Okay, and this is independent of threshold. So here I'm not choosing any threshold. I'm just plotting the performance of the model. We can go and we can discuss how individual here at another moment, how I do this type of plots. Any questions? Any last question? Yes.
Just a quick one, regarding you're saying the system
Yes.
need to consider having more zeros than one so that it can give you a product that is zero, which is what they're looking for.
Yes, so the data set in this case was not that imbalanced. It was around 100 zeros and 300 ones. The only particularity is that you usually are in the contrary situation where you have 100 are ones and the 300 are zeros, because usually most activities are difficult to find them. So if it's like around this proportion, which is like 30% of one class, that's good enough. You shouldn't worry too much. If you get below 30 or 20% of one specific class, then you may need to balance the model. So you can either just withdraw part of the data, so you can take off molecules that are ones, so just to make them more equal, or you can try to expand your data set on the inactives part with other data. So if it's between 20 and 30% of one class at least, that's not a big problem. But below that, you should worry and